in this exercise here, we are going to solve a bunch of recurrences. The R group, we are going to solve these three first, and then we're going to solve another three separately. The reason we are going to solve all this at the same time is because in the left-hand side you have the same expression, right? Even this one that looks different, it can be written like this. You can shift one unit the index, and then you have this 5 times 5 to the power n, and n is larger than or equal to 0 according to this, and of course a0 doesn't change. This is a0 equal to 1, and this way you can see that it's got exactly the same form as the previous one. So the general form that we have here is an plus 1 minus an is equal to cn, and cn is some given sequence, which is different in the three cases, right? And this is valid for all n larger than or equal to 0. And a0 in all three cases is equal to 1, right? So we're going to focus on this general structure, and then we're going to particularize for the three examples and solve it, right? So let's begin with this. The standard procedure is n plus 1 is the highest index that you have here. So you multiply the whole equation by z to the n plus 1, right? N plus 1 minus z n plus 1 an equal to cn z n plus 1, right? And then you sum in the whole range of the index n. So what you have here is the sum from n0 to infinity z n plus 1 a n plus 1 minus the sum from 0 to infinity z n plus 1 an, right? And here we have z n plus 1 from 0 to infinity, right? This is a standard manipulation that we do to transform this equation into an equation for the generating function. By the way, the generating function we're going to deal with is the sum from 0 to infinity of an z to the n. This is a standard. This is the ordinary generating function of the sequence an, which is the sequence we want to find from 0 to infinity. All right? Okay, all we have to do now is to write this in the appropriate form in order to identify first the generating function in these terms, and second the function that we have here. Okay. Well, let's begin with this, right? First, in this bit here, we're going to shift 1 unit down the index inside and 1 unit up the index in the extreme. So the sum becomes the sum from 1 to infinity of an z to the n, right? Then this one here, this is fine because you have an here, but there's a z n plus 1, but you can factor out one z, right? Z n plus 1 is z n times z, and z can be taken out from the sum because it doesn't depend on n. So what we have is this expression here is an times z to the n, right? And finally we have this, which we can express if we like, again, factorizing as here, factorizing one z, and then we put this z here, and then we have the sum from 0 to infinity of cn z to the n. So this is a function, I'm going to call it g, that we have to identify in all three cases, right? But these functions here are related to the generating function, the ordinary generating function of the sequence. This one here is almost this one, except for the fact that it begins at a different index. This begins at 1, so the first term, n equal to 0, is missing. But the first term is just a0. So this term here is just fz minus a0. And a0 in all cases is equal to 1, so this is minus 1. And then you have here minus z. And the expression here is directly f. So in the left-hand side, you always have this expression in all these three cases. And in this right-hand side, what you have is this. Okay? Right. Now, the three cases we are going to deal with are, in the first case, Cn is equal to 3 3 to the power n. In the second case, what you have is Cn equal to n squared. And in the third case, what you have is, after the transformation that brings it to the same form as the other two, Cn is equal to n plus 1 times 5 to the n. All right? So we need to identify the function g in all three cases. By the way, this can be rewritten. You put the 1 here in the right hand side and factor out the f. So we have 1 minus z times f equal to 1 plus z dz, right? Which leads to this expression for f is 1 over 1 minus z plus z over 1 minus z times g of z. Okay, so once we identify this function, we already have the function f, and then we can try to expand this expression in order to get this solution, the coefficients, which are the solution to our recurrence. Okay, so let's begin with a. Okay, we have 3 to the n. So what is g of z? G of z is the sum from 0 to infinity, 3 to the n times z to the n. But this is equal to the sum from 0 to infinity of 3z to the n, right? And this is just the geometric series, so this is 1 over 1 minus 3z. Okay, perfect. Then what we have here in this first case is that f is equal to 1 over 1 minus z plus z over 1 minus z, 1 minus 3z. All right? Okay. Now we need to expand this fraction there, right? So what we are going to do is we're going to use the typical expansion in terms of elementary fractions, right? If you have these two factors to the power 1, and here the numerator is a polynomial of degree smaller than the denominator, you know that this can be written as this expansion, okay? 1 minus 3z, right? And in order to determine these coefficients, what you have to do is you multiply by this denominator here. So you multiply and you get z equal to a times 1 minus z cancels, so we have just 1 minus 3z. And here 1 minus 3z cancels, and then we have just b times 1 minus z. This expression is valid for every z, so we take z equal to 1, and if we do that, this factor goes away. And here we have 1 on the left hand side equal to, if z is 1, this is negative 2, so minus 2 times a, which leads to a equal to minus 1/2. And if we make z equal to 1/3, then this factor here is 0, so we have 1/3 here equal to 1 minus 1/3, which is 2/3, right, times b, or b is equal to 1/2. And from this 2, what we know is that this fraction here is equal to, so z over 1 minus z times 1 minus 3z, this is equal to 1/2, which is a common factor of 1 over 1 minus 3z minus 1 over 1 minus z, right? Remember, this is minus 1/2, so it's the coefficient here, okay, the coefficient of 1 over 1 minus z, right? And the other one is minus 1/2, sorry, it's plus 1/2, so this is the coefficient that you have here. So this is the, once we put this here, this is this fraction, so we have still to add this one. You have 1 times this fraction, you have minus 1/2 this fraction, so this is 1/2 times this fraction, okay, after you cancel one with the other, plus 1 over 1 minus 3z. All right, so that is the final expression that we're going to use for the function, right? And now what we have to do is to expand this expansion, right? This expression, in order to identify the coefficients. But that is easy because in both cases what we have is just the geometric, the sum of the geometric series. So the expansion of that is straightforward. This is 1/2 of the sum from 0 to infinity of z to the n plus 1/2 the sum from 0 to infinity 3 to the n z to the n. Okay, this is the denominator, 3z, right? Okay, so we group these together in just a single sum, and then we have the sum from 0 to infinity. Z to the n is a common factor in the coefficient, so you have 3 to the n plus 1 over 2 times z to the n, right? So the conclusion is an is equal to 3 to the n plus 1 over 2. Okay, that is the solution to our first case, our first problem. Now let's go to case B, right? In case B, our function g is, well, go up here, Cn is n squared, so we put it here, right? So we have n squared set to the n. So g is equal to the sum from 0 to infinity of n squared set to the n. So we need to identify this function first, right? Okay, we're going to use, there are many ways of trying to figure out what this is, but perhaps the simplest way is the following. It's use derivatives of a known function. Let's take this function here, let me call it h, okay? It's going to be 1 over 1 minus z, which is just the sum from 0 to infinity z to the n, right? Now, if we take the derivative of h, we can take the derivative both in the function and in the series, term by term. So from here, we get that h prime is equal to, on the one hand, is 1 over 1 minus z squared, okay? And on the other hand, you have here the sum from 0 to infinity of n z n minus 1. All right? By the way, when n is equal to 0, this term is 0, so we can just start at 1. Okay? Well, it makes sense because the derivative, the first term is a constant and the derivative of a constant is 0, so the first term disappears. And we can rewrite this expression by increasing 1 unit this index and decreasing this one as this. N plus 1. Well, actually, no, we're not going to do this. What we're going to do is the following. So we have this expression, okay? And we're going to multiply just by z, right? So multiply this by z. Okay. What you get is the sum. Well, you get, on the one hand, if you multiply this, you get z over 1 minus z squared, right? And on the other hand, if you multiply this, you get the sum from 0 to infinity of n times z to the n, okay? You see, we started off from this series here, and doing this operation, taking the derivative and multiplying by z, we get this series, which is similar to this one, but it's multiplied by n. Here we have n squared, not n. But it's clear that we can repeat the same trick with this this series here, and then we get the n squared that we need, right? So we're going to do the same with this. So we take another derivative, okay? So we take the derivative of this function, right? Let me just put it for the time being like this, minus z squared prime. And if we take the derivative, we have the sum from, well, by the way, this was 1, okay? This was 1, right? We have the sum from 1 to infinity of n squared z n minus 1. And if you multiply by 1, by z, sorry, if you multiply by z, so if I do this, h prime z prime, which is z times the derivative of this function, whatever it is, we'll calculate it in a moment. What you get is the sum from 1 to infinity of n squared z to the n. Well, it doesn't seem quite this one, because this begins at 0 and this begins at 1, but obviously the term n equal to 0 does not contribute because it's 0. So actually you can just remove this first term and put 1 without losing anything, right? And now we have exactly what we want. This is g of z. But the good thing about this is now we have an expression to calculate g of z, right? It's this one. So we have to do this derivative here. Okay, so let's do that, right? So let's take the derivative of this. The derivative of this is, this is a quotient, so you have derivative of z is 1 times this, so 1 minus z squared, minus z times the derivative of this, which is 2 times 1 minus z times minus 1, so plus. All right? And then you divide this by 1 minus z 4, right? Which is the square of the denominator. Well, there is one common factor here, 1 minus z, which cancels ones there. So you have 1 minus z here, plus 2z, right? And down here you have 1 minus z cubed, okay? And the subtraction of these two terms gives 1 plus z over 1 minus z cubed, right? Okay, this is the derivative, okay? If we multiply by z, we obtain g. So g is equal to z 1 plus z divided by 1 minus z cubed. All right? Okay, we have the function f, the function g. So we need to calculate the function f. The function f is related to g with this formula here, right? So we have to write 1 minus z, 1 over 1 minus z, and then we have to add z over 1 minus z. Where is it? Yeah, z over 1 minus z times g. And if we do that here, what we have is z squared 1 plus z over 1 minus z 4. Okay. So this is our function, and now what we have to do is to expand this, right? But expanding this function requires transforming this into elementary fractions, okay? Well, let me first, because I think it's going to be easier, let me first reduce this to just a common fraction, right? By multiplying here by 1 minus z cubed, okay? So we have 1 minus z cubed plus z squared plus z cubed, right, divided by 1 minus z4, right? This is a common denominator. And if we expand the numerator here, the numerator is 1 minus 3z plus 3z squared minus z cubed, right? This is the expansion of this binomial, and plus z squared minus plus z cubed, right? Okay, you have z cubed here, they go away. So what we have up here is 1 minus 3z plus 4z squared. All right, so f is 1 minus 3z plus 4z squared over 1 minus z 4. All right. In order to expand this function, what we need to do is to, well, actually, well, we can do two things. One is expanding this into elementary fractions. That's one. The other one is what I'm going to do is to, I'm going to do the following. You have this polynomial up here, right? Let's call this p. Is 1 minus 3z plus 4z squared. What I'm going to do is to expand this polynomial in powers of 1 minus z, or z minus 1, right? In powers of z minus 1. How do I do this? Well, there are many ways. Perhaps the simplest is the following. Z is equal to z minus 1 plus 1, right? Okay. So I can replace this here directly instead of z. Now, z squared is z minus 1 plus 1 squared. I can take this as a binomial of these two terms, and then I have z minus 1 squared, right? Plus 2 times z minus 1 plus 1. And then I can put it here, right? So this polynomial is then 1, okay? Minus 3 times this, so minus 3, because of this one, and then minus 3 times this, which is plus 3 times 1 minus z. Okay, if I change the sign of this. And then I have 4 times z squared, which is 4, right? 4 times 2 is 8. 8 times z minus 1, which is minus 8, 1 minus z, right? Changing the sign here. And then I have 4 times this, so plus 4 times z minus 1 squared or 1 minus z squared. It doesn't matter because it's a square, right? And if I simplify this, what I get is 1 plus 4 is 5, minus 3 is 2, okay? Then 3 minus 8 is 5, 1 minus z, and finally I have 4, 1 minus z squared. If I put this back here, what I have is this. I have 2 minus 5, 1 minus z, plus 4, 1 minus z squared, divided by 1 minus z 4. I can split this into 3 fractions. First fraction is 2 over 1 minus z 4, okay? The second fraction is 5 over 1 minus z cubed, right? I'm canceling 1 factor 1 minus z here and here. And the third fraction is 4 over 1 minus z squared. I'm canceling 2 factors from here and there. Now I have this expanded in this way, right? And in this way it's easy to determine what are the coefficients, because we know the expansions of these fractions here. We know that 1 over 1 minus z to n plus 1 is the sum from 0 to infinity m plus n over n z to the n. Okay, we know this expansion. Okay, so we're going to apply this to these 3 expansions there. So f is equal to 2 times the sum from 0 to infinity. M is 3 in this case, right? Here's n plus 1. So if n plus 1 is 4, m is 3. So what we have here is 3 plus n or over 3, doesn't matter, right? You know, these two coefficients, these two binomial coefficients are identical. Then z to the n here. Then we have minus 5, the sum from 0 to infinity. Now m is 2, so we have 2 plus n over 2, right? Z to the n. And finally, the last one is 4 times the sum from 0 to infinity. And what we have here is 1 plus n over 1 z to the n, all right? Okay, if we group these 3 expressions together, what we have is a unique coefficient, which is 2 times 3 plus n over n minus 5 times 2 plus n over n plus 4 times n plus 1 over 1 times z to the n. And then we can identify our an with this expression here. Well, sorry, I'm writing n here. This is okay, right? But the way I'm writing it here is 3, 2, and 1. Okay? Doesn't matter much because the value doesn't change, right? What I'm going to do now is to simplify these expressions, because these expressions are easier to write explicitly. So an is equal to, let's begin here, right? N plus 1 over 1 is just n plus 1. So this is 4 times n plus 1 minus. Then I have here 5 times, and then I have this. It's n plus 2 times n plus 1 over 2 factorial, right? And finally I have that, which is 2 times n plus 3 times n plus 2 times n plus 1 over 3 times 2, so 3 factorial, all right? Well, the 2 of course cancels, in this case, right? And you see what we have here. We can factor out n plus 1, right? n plus 1 is common to the three factors. So what we have is 4 minus 5/2 times n plus 2 plus 1/3 n plus 2 n plus 3. And just to remove the denominators, what we're going to do is to multiply everything by 6 and divide by 6 here. So it's n plus 1 over 6. And we multiply this by 6, we get the 24 here, minus 15, n plus 2, plus 2, n plus 2, n plus 3. All right? Okay, so now we just need to expand this. So this is equal to n plus 1 over 6. And we have here 24 minus 15n minus 30. And then plus 2 times n squared plus 5n plus 6, right? Which is, all this is 2n squared plus 10n plus 12. All right? And now we need to simplify this. This is n plus 1 over 6. We have here 24 plus 12 here is 36, minus 30 is 6. So we have 6 here, right? Then we have minus 15n plus 10n, that's minus 5n, okay? And finally, I have 2n squared here, so plus 2n squared. So my last expression for the coefficient an is equal to this, is n plus 1 times 6 minus 5n plus 2n squared, right, over 6. Let me put it cleaner. So n plus 1 times 6 minus 5n plus 2n squared, right, over 6. Okay, you can put it even cleaner if you factorize this, right? And to factorize that, what we have to do is to find the roots of this second order equation. So the roots of this are n is equal to plus minus 5, well, sorry, to plus 5, plus minus square root of 5 squared is 25, minus 4 times 2 times 6, which is 48. But turns out that this is an irreducible quadratic factor because you have complex roots here, so well, you can forget about this. This is then the final expression for the coefficients here. All right. This is B, and we now need to solve C, right? For C, what we have is this coefficient. Okay, so let me copy it. This coefficient here, and we're going to copy it here, right? Okay, so there's an n missing here, right? So the function g is the sum from n0 to infinity of n plus 1, 5 to the n, z to the n. All right? Okay, which is the same as the sum from 0 to infinity of n plus 1, 5z to the n, right? Well, again, to identify this, what we need to do is, again, take this function, h of w, which is the sum from 0 to infinity of w to the n, right? And using w, because what we have here is 5z, not z, right? So this is what is going to be w, right? And what I'm going to do is to take a derivative here. So I calculate the derivative. And as I said before, this is the sum from n, w, n minus 1, right? From n0 to infinity. And again, for n equal to 0, I can remove the term because it's 0. Okay, so I can begin at 1. Okay, and now I can shift this, right, 1 unit down in this index and 1 unit up here, and transform this into this expression, which is exactly what we have here. Okay, so it turns out that this function here is the derivative of this one, but this one is known. This is 1 over 1 minus w, and its derivative is 1 over 1 minus w squared. Okay, so what we have here, g, is simply this function evaluated at 5z. So we have 1 over 1 minus 5z squared. All right. So now we introduce this in the formula for f, which is 1 over 1 minus z plus z over 1 minus z times 1 minus 5z squared, right? Okay. And if we want to expand this, what we have to do is to express this as a, to expand this in elementary fractions, right? So let me just take this fraction here. This is a square, right? Take this fraction here and decompose it into elementary fractions, right? And you know, the way to do this is you have two factors, so you have to introduce fractions for every factor. So the first factor is this. You have one fraction like this because the exponent is 1, but here the exponent is 2, so you need to introduce two fractions. The first one is this with exponent 1. The second one is this with exponent 2. So you have to introduce as many fractions here as there is exponent here, starting from the exponent 1 up to exponent whatever you have here. So we have these two fractions in the expansion. Okay, now we multiply this in the two sides, and then we get z on the left hand side, and on the right hand side we have a times 1 minus 5z squared. Here we have b times 1 minus z, 1 minus 5z, right? Because there's only one factor and we are multiplying by 2. And here we have c multiplied by 1 minus z, right? Because the 1 minus 5z squared disappears. So it turns out that we have to choose a, b, and c, so that this expression here is just z here. This should be valid for every z, so you can take particular values of z. So for instance, if we take z equal to 1, this goes away, and then we have just this factor. So we have 1 on the left hand side, and on the right hand side we have 1 minus 5, which is minus 4. The square is 16, so we have 16a. So a is equal to 1 over 16. Okay, 1 over 16. Right, now we take z equal to 1 over 5, okay, and this factor cancels, this factor cancels. We just have this one surviving, so we have 1/5 is equal to c times 1 minus 1/5 is 4/5. So c is equal to 1/4, all right? Okay, there's no way to obtain in b if we have this, but what we can do is we're going to introduce these terms, these numbers that we have obtained here, and simplify what we get, right? So we have z in this side, and that is equal to 1 over 16, 1 minus 5z squared, plus 1/4, 1 minus z, and then we have b times 1 minus z, 1 minus 5z, right? And we need to simplify now, so we just eliminate that. So b times 1 minus z, 1 minus 5z is equal to, and well, actually we can multiply by 16 just to get rid of the denominators. So we multiply by 16, and then we have 16z, right, minus 1 minus 5z squared minus 4 times 1 minus z, okay? And we need to simplify this. So we have 16z here minus, we expand this binomial, that is 1 plus 10z minus 25z squared minus 4 plus 4z, right? Which becomes, let's see, you have minus 1 minus 4 is minus 5, okay, it's minus 5. Well, let me just begin with the constant. So we have minus 1, yeah, minus 5, okay, that's okay. So this one and this one. Then we have the term with z, which is 10 plus 4 is 14, no, sorry, 10 plus 4 plus 16, right? So that's 30, is that right? It's 14 plus 16, that is 30, right? So plus 30 z. And finally, we have minus 25 z squared. Well, this is easily, well, you can easily factor 1 negative 5, and then we have 1 minus 6 z plus 5 z squared, right? Okay, right, now look at these two factors here and multiply them out. So we have 16b is equal to, multiply by 1 minus this times this plus this times this is 6z, and this times that is plus 5z squared. That is equal to minus 5, 1 minus 6z plus 5z squared. And as you can see, this factor is common. So we end up with b being minus 5 over 16. Now we have all three coefficients, right? So this expansion here is equal to, I can factor out 1 over 16 here. 1 over 16 is 1 minus over 1 minus z, right? Now b is minus 5, okay? It's minus 5 over 1 minus 5z. Well, I can get rid of the bracket, it's not necessary. So 1 minus 5z. And finally, c is 1 over 4, which is 4 over 16, right? So it's plus 4 over 1 minus 5z squared. Okay? Right, this is this fraction here, which is here. So we have to add 1 over 1 minus z to this expression here. So finally, f is 1 over 16 multiplying, if I add 1 plus 1 over 16, this is 17 over 16. So I have 17 over 1 minus z minus 5, 1 minus 5z plus 4, 1 minus 5z squared, right? See? Okay? So that is the fraction I end up with, okay? And now I have to expand this. But I know the expansions of everything, right? I have first, well, I can write it like this. This is, let's say, 17 over 16, okay? And I have just the geometric geometric series. So this is the sum from 0 to infinity, z to the n, right? This is this one here. Here we also have the geometric series, but the argument is 5z, so this is minus 5 over 16, the sum from 0 to infinity of 5 to the n, z to the n. And finally, I have this, which is 4 over 16, which is 1/4, right? And then I have this fraction, this is 1 over 1 minus w squared, and that is, remember, this is the sum from n0 to infinity of n plus 1 over n z to the n, and n plus 1 over n is just n plus 1, not z to the n, sorry, w to the n. Okay, so this is the sum, 0 to infinity, n plus 1, and then w, which is 5z, so it's 5 to the n, z to the n. All right, so an is just 17 over 16 minus 5n plus 1 over 16 is 5n plus 1 because I'm multiplying 5 by 5 to the n, right? Plus n plus 1 over 4, okay, n plus 1 over 4 times 5 to the n. Okay, this is the final solution for the coefficients of this recurrence here. It's a bit more complicated. I mean, no, not complicated, but it takes longer to figure it out. But the result is, I mean, can be obtained just as in the other cases, right?